Hello, my name is Brandon Mariga, and in this video I will be providing a brief overview on carbon nanotubes. I'll be touching on their basic structure, the events that led up to their discovery, notable research involving them throughout the years, and their current applications. Carbon nanotubes are made from rolled sheets of graphene. Graphene is a two-dimensional hexagonal array of carbon held together with sp2 hybridized bonds. This hybridization gives rise to strong sigma bonds within the plane of the sheet as well as pi bonding orbitals that are outside of the sheet plane. Both the geometry and bonding of this molecule give it amazing properties, such as high stability, a strength that is 50 times stronger than steel, and a conductance that is nearly 1,000 times greater than copper. Carbon nanotubes have been reported in major journals since the 1950s. However, it wasn't until the discovery of fullerenes that they had a reason to be actively researched. In 1985, Richard Smalley, Robert Curl, James Heath, and Harold Kroto began working with astrophysicists to determine the origins of long linear carbon chains called polyenes that had been found in interstellar space. They believed red giants were the source. Red giants are massive stars that are in the last stages of their life cycle. They form whenever a main sequence star runs out of hydrogen to turn into helium via nuclear fusion. Once this process stops, the outward pressure produced by fusion gives way to the inward pressure of gravity and the star becomes compressed. As the star is compressed, its internal temperature rises to over 100 million degrees Kelvin, which allows the nuclear fusion of helium into carbon. The energy that is produced by helium fusion causes the star to expand outward to diameters of over 100 billion kilometers. In order to determine if polyenes were present in the red giants, Harold Kroto and his group collected the star's emitted infrared spectra and compared these to the infrared spectra of various polyenes. This process involved synthesizing their own polyenes, which posed a problem. Polyenes were extremely difficult to effectively synthesize during this time period. To provide a solution to this problem, the group of scientists developed a procedure to produce polyenes in great yield, which involved shooting a high-powered laser at samples of graphite. However, upon mass spectrometry analysis of their products, they noticed a high-intensity peak at 720 atomic mass units. This peak corresponded to C60, or more formally called Buckminster fullerene. Scientists were ecstatic about the discovery of a new allotrope of carbon, especially due to the 60 different places where functional groups could be added. This promised a whole new class of molecules with unknown properties waiting to be discovered. By 1991, methods for synthesizing fullerenes were improved, and a group headed by Sumio Ijima at NEC in Tokyo was tasked with investigating the growth mechanism behind fullerenes. However, upon characterizing their products, Dr. Ijima noticed something odd in the transmission electron microscopy images. There were needle-like structures present. These structures turned out to be multi-walled carbon nanotubes. Sumio Ijima published his findings in Nature magazine, where he detailed the process of the multi-walled carbon nanotubes and their characterization data. The nanotubes were synthesized through a process called arc discharge evaporation. Basically, this process involves hooking up a graphite cathode and anode to a power source. You turn on the power source and bring the cathode and anode within close proximity towards one another. This creates an arc current that puts out enough heat to turn into plasma. The plasma then evaporates the anode into carbocations, which react with one another and collect the soot in the chamber on the cathode. The soot was then characterized using two similar techniques: transmission electron microscopy imaging, or TEM for short, and electron diffraction analysis. In transmission electron microscopy imaging, a beam of electrons is generated, focused and passed through a sample. Here the sample must be thin enough to be electron transparent, which, for conventional TEM instruments, is 100 nanometers or less. For comparison, the image in the upper right shows a sample with a thickness of only 300 nanometers. Once the beam of electrons begins to pass through the sample, they can pass through to a detector or be scattered by the nuclei of the atoms that make up the sample. It turns out that thicker portions of the sample will have a higher probability of scattering more of the incident electrons than thinner portions. This means that in general, thinner portions of the sample allow a high amount of incident electrons to pass through to the detector, while thicker portions of the sample only allow a small number of electrons to pass through to the detector. All of the electrons that make it to the detector combine to make a single image, where thicker portions of the sample appear darker in contrast than thinner portions. This can be seen in the sample structure in the lower right, where an imaginary 3D structure on the left will produce the hypothetical TEM image on the right. Whenever Dr. Ejima performed TEM imaging on his carbon nanotubes, he found that they were 4 to 30 nanometers in diameter and up to 1 micrometer in length. To put this into perspective, the average diameter of a tip of a sewing needle is 0.74 millimeters, which is 6 orders of magnitude greater than the diameter of the nanotubes. All of the nanotubes were multi-walled, which means that the nanotubes had smaller nanotubes inside of them, similar to Russian nesting dolls. The number of nested tubes that were observed ranged from 2 to 50. The thinnest nanotube that was observed was composed of 2 nested nanotubes, whose inner diameters consisted of 5.5 nanometers and 4.8 nanometers. The 2 nested tubes were separated by a distance of 0.34 nanometers, which is the exact distance between 2 sheets of graphene within a sample of bulk graphite. One of the smallest nanotubes observed displayed an inner diameter of 2.2 nanometers and was part of a 7-sheet nested nanotube. In the displayed images, you can see some of the actual TEM images that Dr. Ejima took, where the viewing plane of the images is noted in the red tube cartoon. Once the basic shape of these nanotubes was determined, the scientists wanted to determine their specific geometry. In other words, how are these tubes rolled from graphene sheets? Sumio came up with 2 possible geometries, a staggered orientation and an end-to-end orientation. If you were to roll this generic graphene sheet so that point A meets point C, you would get the end-to-end orientation. But if you were to roll it so that point A meets point A prime, you would get the staggered orientation. To test which orientation the nanotubes were in, the researchers used electron diffraction analysis. This basically works by firing an electron beam at your sample, where the electrons will interact with the sample atom's electron cloud or hit the atom's nucleus and get scattered. This produces symmetrical dot patterns that can ultimately be analyzed to determine the crystal array of your sample. Since the shape of nanotubes are symmetrical, Dr. Ejima noted that if you fire the electron beam at the top of a nanotube and out through the bottom, you can determine which orientation that they are in based on the number of diffraction patterns that are present. For example, since the end-to-end orientation will have the same atomic arrangement at the top and bottom, only a single diffraction pattern will be produced. However, if the tubes are in the staggered orientation, then the atomic geometries are different for the top and bottom of the tubes. Therefore, you should observe 2 separate diffraction patterns. Since all of the nanotubes were multi-walled, Dr. Ejima simply counted the number of diffraction patterns that were produced by each sample. If the number was odd, then he knew that his sample was in the end-to-end orientation. But if the number was even, then he knew that his sample was in the staggered position. Vast numbers of nanotubes were analyzed, and the primary consensus was that most of the tubes were in the staggered orientation. Sumio Ejima's paper took the scientific community by storm, as this was the first time that anyone had successfully characterized carbon nanotubes. This sparked an interest in a multitude of follow-up studies. The first that I will cover is the notable advances in carbon nanotube synthesis. A few years later, in 1993, both Sumio Ejima and Donald Bethune independently discovered how to go from making multi-walled carbon nanotubes to single-walled carbon nanotubes. After Ejima's characterization of multi-walled carbon nanotubes in 1991, he continued his research in attempts to find a more controlled procedure for producing nanotubes with tailorable geometries. In his follow-up study, he was able to mass-produce single-walled carbon nanotubes, which ranged in diameters of 0.7 to 1.6 nanometers. As seen in the histogram, nanotubes with diameters of 0.8 and 1.05 nanometers were the most prevalent. The images to the right display transition electron microscopy images of the single-walled nanotubes. Dr. Ijima was able to achieve a selective large-scale synthesis of single-walled carbon nanotubes by altering his original arc discharge evaporation technique. This involved adding methane gas to the evaporation chamber and solid iron filings on top of the cathode, where upon discharge the iron would melt and form an iron vapor. Ijima created this technique based off the catalytic role iron played in the production of carbon fiber at that time. However, he was uncertain as to exactly how the presence of iron preferentially assisted the formation of single-walled carbon nanotubes. Donald Bethune also synthesized single-walled carbon nanotubes by using relatively the same experimental procedure as Ijima. However, iron, nickel, and cobalt metal filings were used. His initial aim was to synthesize metallofullerenes and graphite-encapsulated nanocrystals. However, upon TEM analysis, he observed that his product was primarily single-walled carbon nanotubes with diameters of roughly 1.2 nanometers, as shown in the first figure on the left. The round spheres that can be seen sticking to the sides of the carbon nanotube were determined to have diameters that correspond to fullerenes that range between 60 to 100 carbons. This showed that although single-walled carbon nanotubes could be produced, they could not be purified and collected. In 2004, Zhang and his group of researchers reported that they grew single-walled carbon nanotubes up to a length of 4 centimeters on a silicon substrate using a process called catalytic chemical vapor deposition. This process involved the decomposition of ethanol vapor using FeCl3 as a catalyst, which took place inside a quartz tube furnace with a continued flow of hydrogen and argon gas. A sample of a single-walled carbon nanotube can be seen in the figure to the left, where a roller is held against an image of a nanotube created by superimposing 230 separate TEM images. The diameter of the nanotube was measured using atomic force microscopy, which is shown to the figure at the right. Here, the height represents the diameter, which is 1.4 nanometers. Another key accomplishment in this study was that Zhang's alternative synthesis produced pure, single-walled carbon nanotubes without the presence of fullerenes or multi-walled nanotubes. This was a direct solution to the problem experienced in Ijima's and Bethune's previous studies, which tremendously helped with the progress towards synthesis optimization. In 2005, Mei Zhang and a group of scientists at Nanotech decided to take a different approach to growing carbon nanotubes. Instead of aiming for longer lengths, they managed to synthesize a multi-walled carbon nanotube sheet that was 1 meter long and 5 centimeters wide. The carbon nanotubes were grown in vertical forests by catalytic chemical vapor deposition, where their lengths were generally kept within 70 to 300 micrometers. Once these forests were purified, an adhesive strip was used to peel away strips of nanotubes oriented in sheets. Multiple sheets were then stacked on top of one another to form densified sheets, which displayed tensile strengths of up to 465 megapascals per gram per centimeter cubed. At the time, this was much stronger than the 160 megapascals per gram per centimeter cubed tensile strength of mylar and Kapon films used for lightweight aircraft vehicles. In Figure A, we can see a photograph of a multi-walled carbon nanotube sheet that was hand-drawn from a nanotube forest at an average rate of 1 meter per minute. Its transparency is illustrated by the Nanotech logo placed underneath of it on the table. In Figure B, we have an SEM image which captures a nanotube forest being drawn into a sheet. In Figure C, we have another SEM image where we can see the nanotubes of a forest beginning to form a sheet. In Figure D, we have yet another SEM image that shows 4 nanotube sheets stacked on top of one another, each of which are placed at 45 degrees relative to the sheet below it. Here, the mass of the droplets are roughly 50,000 times the mass of the densified sheet. In 2013, Matteo Pasquale and researchers at Rice University took the carbon nanotube sheet a step further and successfully spun carbon nanotubes into multifunctional nanotube fibers out of nanotube forests. These fibers exhibited elongation up to 1.5% of their original length before snapping, a tensile strength of up to 1.3 gigapascals, and a high conductivity of 2.9 millisiemens per meter. In Figure A, we can see a high magnification SEM image of a fiber. In Figure B, we can see a low magnification SEM image of a fiber. In Figure C, we can see a 46-gram LED being lit and suspended by only two 24 micrometer thick carbon nanotube fibers. Finally, in Figures D and E, we can see SEM images of the cross-section of a carbon nanofiber, where Figure D is a magnified image of a section in Figure E. This is meant to show the density of the fibers, where voids are nearly absent and only exist in less than 100 nanometer diameters. I briefly touched on the idea that carbon nanotubes can display electrical properties in that last example. So in the next portion of this video, I would like to dive into some of the notable discoveries and applications of the electronic properties of carbon nanotubes. In addition to all of the synthetic advances since Ijima's characterization of carbon nanotubes, numerous scientists have worked diligently to study and exploit their electrical properties. In 1997, Mark Bockrath and his group measured single electron transport through short bundles of single-walled carbon nanotubes. Prior to this study, only theoretical predictions on nanotubes' electrical properties could be performed, as there was not yet a consistent method in producing single-walled carbon nanotubes with desired dimensions. However, due to recent advancements, in 1997 they were able to lithographically synthesize short ropes of the nanotubes with diameters of 1.4 nanometers. Bockrath measured the conductance of the nanotube ropes as a function of gate voltage, which displayed sharp peaks that varied in intensity as seen in Figure A. These peaks indicated that the nanotube ropes acted as a transistor, where certain applied voltages would allow the flow of electrons, while others prohibited the flow of electrons. Figure B shows the temperature dependence of one of the peaks. It should be noted that this figure corresponds to a different sample run than the one that generated Figure A. Figure C displays the width of the peak in Figure B as a function of temperature. This shows that the peak width increases linearly with temperature. Overall, this study served as one of the major breakthroughs needed for showing that carbon nanotubes could be worth applying to functional electronic devices. In 2006, Yang Chen and his team published a paper from IBM announcing that they had successfully built an electronic circuit around a single-walled carbon nanotube. In this circuit, they were able to attach 12 field effect transistors along the length of a single nanotube that was 18 micrometers long, as seen in Image A. Chen tested the circuit by performing a ring oscillator test. This involves oscillating a voltage output between two values, which represent true or false in the realm of computer science where AC voltages are used. The output signal of the oscillator was measured as a function of supply voltage as seen in Figure B, where a resonance occurred at 13 MHz for a supply voltage of 0.5 volts. Whenever the supply voltage was increased, the resonance frequency also increased, up to a resonance of 52 MHz at 0.92 volts of supplied voltage. This profound accomplishment paved the way towards the development of future nanocircuits integrated with single-walled carbon nanotubes. After a couple of years had passed, researcher Aaron Franklin and his team from IBM announced in 2012 that they had successfully synthesized an extremely small carbon nanotube transistor that was capable of outperforming silicon-based transistors. As seen from the TEM images in Figures B and C, the new nanotube transistor contained cross-sectional channel lengths that were just under 10 nanometers, which was something that silicon could not achieve without sacrificing some control over the electrical current. Their sub-10 nanometer transistor achieved a diameter normalized current density of 2.41 milliamps per micrometer at a low incident voltage of 0.5 volts, which was nearly 4 times as great as what the best competing silicon-based transistors were capable of offering. Franklin's sub-10 nanometer carbon nanotube transistors opened the door to numerous areas of further research, and it was not long before these transistors were applied to even more complex circuits and applications. In 2013, Subhasish Mitra, Philip Wong, and their fellow graduate students from Stanford University built a basic computer which ran on a processing chip constructed entirely of sub-10 nanometer carbon nanotube transistors. Shown is an image of the processing chip that they used, where each unit is packed with carbon nanotube transistors, as seen in the SEM sub-image. The fabrication of the processing chip was insensitive to the relative distribution of nanotubes within each unit, as seen in the nanotube spacings in the SEM image. This tells us that improvements to the fabrication process will have to be made to construct more ordered, viable chips for everyday operations. However, this imperfect chip still enabled the computer to run stored programs and offered completely reprogrammable capabilities. The operating system was also capable of multitasking through a style known as cooperative multitasking, which is where a process momentarily yields control to allow other programs to run. This back and forth switching of control creates the illusion that both programs are running at the same time without dealing with the processing stress of actually running simultaneous programs. This study was extremely important as imperfections in the geometries of carbon nanotubes prevented anyone from building complex circuits from this material up to this point. With the demand for more transistors on computer chips of reasonable sizes, the only solution appears to be shrinking the size of the effective transistors. This study showed that a viable replacement to silicon transistors could very well be carbon nanotubes within the near future. In the final part of this video, I'm going to give a brief overview of our current applications of carbon nanotubes. In April of 2017, when Quan Yang and co-workers at the University of Science and Technology of China used conducting carbon nanotubes in impact-resistant polymers to create a smart Kevlar composite with enhanced ballistic and stab resistance. This could potentially solve the current problem of Kevlar-only dependent body armor, which is the Kevlar can stop a bullet from piercing its wearer, but all of the kinetic energy is still transferred to a single point on the body, which can cause blunt force trauma. With the incorporation of impact-resistant polymers, which stiffen when applying strain, the kinetic energy of a bullet can be spread out over a larger area as opposed to a single point on the wearer's body, which reduces the risk of blunt force trauma. With the incorporation of conductive carbon nanotubes, we can still maintain the lightweight and flexible properties of Kevlar-only body armor, but now with the extra potential to detect points of impact. This sensing capability could potentially be used to immediately notify medical services or call for backup whenever the wearer has been shot. As of 2013, a new series of corrosion control coatings containing carbon nanotubes is being developed and tested. These coatings have the potential for enhanced strength and electrical conductivity due to the properties of carbon nanotubes, while the incorporation of sacrificial metals such as zinc, aluminum, and magnesium offer corrosion protection via cathodic protection. These coatings are being developed so that they can be applied using standard painting equipment such as airspray, airless spray, paintbrushes, rollers, and more. The inclusion of carbon nanotubes allows expensive sacrificial metal-filled primers to be formulated at a reduced metal content, which can lead to a cutback on production costs. As of 2014, carbon nanotubes were applied to environmental remediation and water treatment by creating a sponge containing carbon nanotubes, sulfur, and iron. Studies have shown that these sponges are more effective at soaking up water contaminants such as oil, fertilizers, pesticides, and pharmaceuticals. Also, with the incorporation of iron, The sponges contain magnetic properties that allow easy retrieval once their job is done. It has also been shown that carbon nanotubes on their own exhibit strong absorption affinities for wide arrays of aromatic and aliphatic contaminants in water due to their large and hydrophobic surface areas. This has the potential to be used in water treatment plants as an active filter in the treatment process. Thanks for watching. If you have any questions, leave them in the comments below.